Alright, hi everyone. Today we'll be looking at radioactivity, and we'll actually be using the data from a particular source, that source being barium-137M. The M just stands for metastable. Basically means that this radioactive isotope is relatively long-lived. And that's kind of a caveat in this case, since long-lived basically means anything that's probably longer than, I would say, a second or so. So the way that we actually get barium-137M actually comes from a radioactive source called cesium-137. And the only place we find cesium-137 is from reactors, nuclear reactor cores and things like that, the byproducts from the nuclear fission process in nuclear reactors. It generally has a half-life of about 30 years. And the decay channel in which cesium decays into barium-137M and just stable barium-137 is via emitting a beta ray, or an electron in this case. There are two types of channels. It can just go right to the stable barium-137 by emitting basically a high energy electron, or it can go through the second channel of barium-137M by emitting a low energy electron, and then at that state this will kind of remain there for about 153 seconds. This will be your theoretical half-life that you'll compare to when we go and try and find that from the data. After going through some half-lives, the barium will then emit a gamma ray at some energy, some particular energy, and then finally become stable. The way that you can think about this particular transition from barium-137M to barium-137 is similar to how electrons get excited, similar to this state. So this would be the nucleus being excited, one particular nucleon inside the nucleus, just like one particular electron in the electron cloud covering a particular atom. One of them gets excited and then emits a photon in some particular energy range based on the energy level at which this has been excited. For nuclear decays, these are much high energies versus what are called electronic transitions in those electron transitions that we see typically when we look at spectra in the visible range and things like that. So that's a way to think about how that transition occurs, at least for what we're seeing in today's lab. Alright, so what we're expecting to see is an exponential decay in time for the radioactive isotope or metastable state of barium-137. And what we'll do is we'll look at the activity, which would be in counts per minute. So basically we'll have a Geiger counter that will count the radioactive particles that are emitted. It doesn't distinguish between any of the electrons, gamma rays, or alpha particles, or anything like that. But for our purposes, it's just gamma rays. So it just counts whenever that detector gets pinged. And one thing that we will have to do in addition to finding the activity is determine how much background radiation is occurring behind the scene. And we expect that the background there to be relatively low and constant. So when we actually want to just determine what our signal is, we would have to do a background subtraction for that signal. And you'll see that it's very low in the data that I provided. So I've already plotted for you guys in the worksheet the activity as a function of time and provided the trend line as well. I'll ask you to produce another plot, the natural log of the activity as a function of time. That will be kind of interesting to see, and it will follow the similar format that I provided in that particular graph. Just as some things to note, this activity here is the initial activity you see. It doesn't have any sort of significance. It is what it is based on the amount that you have at that given time. Lambda in our exponential is the decay constant, which is related to the half-life of the radioactive substance, and t here is essentially our variable in time. Alright, just some things to note. I know this semester has gone by pretty quick, and we tend to use the same types of symbols to represent various different things in physics. Just note that in this particular case, when we're talking about lambda here, it's the decay constant and not some wavelength, particularly since we're talking about a gamma ray, a photon, that would have a wavelength associated with it. That's not what we're talking about in this particular graph here. Just to note here, the units for the decay constant is in inverse seconds. Alright, so definitely not a wavelength. So from this particular graph, we'll hope to find the half-life tau from the decay constant lambda, and if we do a little bit of algebra and some arguments on finding when we have half the original activity, we can then find this particular equation where the natural log of 2 over lambda gives us the half-life. And here, the half-life itself is given in just time or in seconds. And you can adjust that based on the amount of seconds that you have. If it's a very large number of seconds, you can always convert it to years and things like that. So this is why we get, sort of uranium having millions of years of half-lives versus, this barium, which will have just a few, not even, well, it would be a few minutes in that case, but 153 seconds is all that we'll see. All right. The one thing that I'll have you guys do in the worksheet itself is make sure that you plot the natural log of the activity as a function of time. When we do that, we'll actually find that the graph should be linear in time, and it should give us a linear trend line that we can then extract the decay constant. In this case, the slope m. If we use our y equals mx plus b formula of a straight line, we see that the slope here, m, is equal to minus lambda, or minus the decay constant. And hopefully this decay constant that we find in this particular graph here should be the same as the decay constant that we find up here, if not that dissimilar from each other. Alright, so other than that, I'll show right after I'm done talking just a very, very short time lapse of the decay of barium-137 M over 10 minutes, which should take about 8 seconds in the time lapse video. So I hope you enjoyed this, and have a good summer.